Hello everyone, welcome back to Talking Mac. Today, our topic is within electronic engineering, which is also necessary for mechanical. And what we will be doing today is diodes. So, with diodes, you could ask, what is a diode? Well, simply, a diode is a component designed to conduct current in one direction. For example, look at this picture over here. As you can see, this is a real diode, whereas this is the diode symbol. So in a real diode, you can see that this white area is visible. That is known as the cathode terminal. That is where the the current exits the diode. Whereas the anode is the entering terminal. That is where the current enters the diode. So as a diode conducts electricity only in one direction, let's say, for example, this is our diode, and this is the rest of the circuit with different components. So the current is going to travel in this direction. You can think of the diode as like an arrow pointing in the direction where the current will flow. And also another thing that's important that we have to keep in mind is the direction of the battery. As we know, it flows from positive to negative. The current leaves the battery from the positive, goes through the diode, and enters the negative. Whereas in this case, where if the battery is the same, but the diode is facing the other way, in this case, the current will not pass through effectively. It will stop here and then it'll get sent back out like this. So that is an incomplete circuit, as this area is not without current, therefore it's an incomplete circuit. As mentioned before, the current leaves the positive side of the battery. It goes like this, but then the diode sends it back in this direction. So therefore the circuit doesn't work. So now you should have a basic understanding of how a diode works. It enters through the anode and then it leaves through the cathode. So likewise, in this scenario, the cathode is the one with the white labeling here. So this is the anode and this side is the cathode. So the current goes through like this. It cannot go the other way. As shown before, this is a good description, or sorry, an image of how a diode would work in a circuit. As here you can see, it's positive and negative. The current will move like this, and here we have the anode and the cathode. So the diode is in the right direction, passes through the the bulb, and then the bulb eliminates. That's a good scenario. The current is passed through the entire circuit, so everything's fine. In this case, you can see the positives here, the negatives here. The current leaves the battery through this side, passes through the bulb. However, the bulb does not illuminate until the entire circuit is complete, which cannot happen in this case, as the diode is facing this way. So it sends the current back like this. And that's an incomplete circuit. Why? Because this area is incomplete. There is no current through there. So therefore, the bulb does not illuminate. To help you remember how it works, just look at the symbol of the diode. Or I'll make it a little easier to look at, yes. And think about the arrow. The arrow shows the direction in which the current is allowed to flow. So if the arrow is pointed in this direction, just think that the current flows through a gate. You can think of the diode as a gate. So it enters the arrow, and then the arrow pushes it. It sends it out in this direction. However, if you look at it in this, if the current is coming like this, you can think about this being a door. So the current, it hits the door and it can't get through the gate. It's just to help you remember. So, in an ideal diode, and by ideal, we mean the most perfect diode that can possibly be created, which is unrealistic. It does not exist. But theoretically, what we would like to have. In an ideal diode, when it is forward bias, this is this scenario, where the current easily passes through the diode in the right manner. That is known as the forward bias. So, in an ideal diode, when we set it as a forward bias, the resistance is 0. Now, why? You could ask me. So the explanation is that in any component in a circuit, there is always resistance. A little bit, not always a lot. There could always be a little bit of resistance in any component. And the diode as well, being another component, has a little bit of resistance. So therefore, if 50 amps of current enters a diode, not the entire 50 comes out. It could maybe be like 47 amps coming out. So that's not perfect. We want the whole 50 to come out back again, which is unrealistic. It does not happen in real life, as every component has a little bit of resistance. However, in the ideal diode, there is no resistance at all. So if 50 amps enters a diode, 50 amps comes back as well, which is also known as short circuit. This is a short circuit because the resistance is zero, and as we know from voltage is equal to current into resistance. If the voltage is, let's say, 5 volts, we both know I is equal to V over R. So if R is equal to 0, anything that divides or multiplies by 0 is equal to 0. Therefore, the current will equal to 0, causing a short circuit. Now, if we talk about the opposite of forward base, that is reverse base, this is pretty much known as an open circuit. Just to remind you, this is the reverse base, where the current tries to enter the diode, but it gets stuck. Let me draw a full circuit, just to make it easier. In this circuit, we have positive and negative over there. So the current will leave the battery, and then, as mentioned before, it can't enter the diode, it gets stuck. So therefore, the current goes back, as the diode sends it back. So this area is open. There's no current going through it. Therefore, it is known as an open circuit, which is also equal to infinity resistance. Oops, sorry about that. Infinity resistance. Let's head over to this graph over here and show you what a perfect diode's graph would look like. So for forward base, since there is no current, the current is 0. Therefore, the voltage will be maximum. It's like that. And in reverse, it will look like that. That's the ideal model graph. However, it is really important to remember that real diodes are not real. Sorry, real diodes are not ideal. So a good representation of a real diode is given by a graph known as the Shockley model. What is the Shockley model? The Shockley model shows how a real diode operates, whether it's in a graph or another model, for example. So the equation to find your current through the Shockley model with the resistance and everything holding back the current is I is equal to Is exponential sine V over N V T minus 1. Now, what are these letters and what do they represent? Well, I, we know for one is current. What's Is? Is is the saturation current of the diode. Then what's Vt? Vt is the thermal voltage, which is also known as Kt over Q, which is approximately 26 millivolts. Then T, and that Vt is the temperature, which is supposed to be in Kelvin, the SI units. Then what's the K? The K is known as the Boltzmann constant, which is equal to 1.38 into 10 to the power minus 23. That's just a constant number, but it is important to remember. And Q is the charge of an electron, which is equal to 1.6 into 10 to the power minus 19 coulombs. So let me make that easier to visualize. There we go. And what's N? N is the diode ideality factor, which is usually 1 or 2. Now let's head over to the Shockley model graph. In the Shockley model graph, the current in the diode is most likely to move like this. Where it's pretty much 0 at 1 and 0.5. And after passing 0.5, it starts to go up. Now, as you can remember, in the previous graph, it looked something like this. However, that was the ideal diode, which is unrealistic. Whereas in the realistic diode, it is most probably going to look like this, which is represented by the Shockley model graph. The ideal model is not very accurate. For forward bias. However, the ideal model is easier and simpler to use in circuit analysis. Now we're going to talk about the different types of diodes. Diodes can come in different shapes and forms. For example, light emitting diode, or LEDs, which are more commonly known. These diodes emit light when they are forward based. Then there are laser diodes, which emits a coherent light when forward based again. Then we have photodiodes. This is where the light changes in reverse bias current. And then we also have these funky looking diodes known as Zener diodes. These have a well-designed reverse breakdown voltage. That is all we have for today. Please like, share, and subscribe, and I'll see you in the next episode.